Welcome back to the session. Now I call upon Mr. R. Vineshwaran, Assistant Professor, Department of Mechanical Engineering, Kingston Engineering College, to introduce our keynote speaker, Dr. Muruga Boobathi, Assistant Professor of ME, PSNA, College of Engineering and Technology, Kothandaraman, Nagar, Dindigul, Tamil Nadu. Sir, Vineshwaran, sir.
Yes, sir. Yes, sir. Audible, Kaba?
Yes, sir, you are audible, sir.
Okay. Good afternoon, all. I would like to invite Dr. S. Muruga Boobathi, sir, Assistant Professor, Mechanical Engineering, PSNA, College of Engineering and Technology, Dindigul. He has obtained Bachelor of Degree Mechanical Engineering from Bharata University and ME Thermal Engineering from Satyabama University. He did his PhD Thermal Engineering at Anna University. He published more than 15 international journals. He presented paper in more than 12 international conferences. Received an grant of Tamil Nadu State Council for Technical Education, Chennai in Student Project Scheme in 2018 to 19. He published an Indian patent in the title of Development of Automotive Muffler based on non-noble material in 2021 to 22. He delivered a guest lecture on energy and exergy analysis of thermal power plants in AICT sponsors 1 week STTP organized by Pragati Engineering College of Andhra Pradesh. He delivered a guest lecture on a biodiesel in IC engines in Maharani Polytechnic Colleges, Dharapuram, India. He delivered a guest lecture on a deflection of beams and unsymmetrical bending in Nalla Narsimha Reddy Group of Institution, AICT sponsor of 1 week refresh program, Andhra Pradesh, India. He organized 1 week FDP on dynamics of machine, sponsored by Anna University, PSNA College of Engineering and Technology. He acted as a guest lecturer, a guest editor or members of Journal of Thermal Analysis and Calorimetry of 2018 to 19. He acted as a guest editor or member for Thermal Analysis and Energy Systems, International Mechanical Engineering Congress of organized by the National Institute of Technology, Trichy in India. He reviewed more than 25 papers in various reputed international journals like SCP Scopus Index. It's been honorable introduce such a eminent person, and I would like to welcome you once again, sir. Now I would like to invite Dr. S. Muruga Boobathi, sir, take up on the session. Thank you, sir.
So thank you, sir. Thank you for your nice introduction, sir.
Thank you, sir.
So is my PPT is visible, sir?
Sir, no, sir.
Yes, sir. Yes, sir.
It's not shared.
I think now it is visible, sir.
Not yet, sir. Not yet. Yes, sir. Now it's visible, sir.
Yeah, okay, sir. Good afternoon, everyone. Myself, Muruga Boobathi, Assistant Professor in the Department of Mechanical Engineering in PSNA College of Engineering and Technology, Dindigul, Tamil Nadu. So today my topic is basics of energy of thermal system using cycle tempo software. So introduction, energy. Normally we discuss about the most of the cases in thermodynamic analysis. Most of the cases, the energy analysis we have discussed. So energy is nothing but the capacity for doing work. So the energy may appear in the form of potential, kinetic, thermal, electrical, chemical, nuclear, or other various forms. So most probably we are using the energy as a heat and in the form of work. So thermodynamics permits the behavior, performance, and efficiency to be described for the systems for the conversion of energy from one form to another form. So normally the conventional thermodynamic analysis based primarily on the first law of thermodynamics, so which states there's a principle of conservation of energy. An energy analysis of an energy conversion system is essentially an accounting of the energies entering and existing. So the existing energy can be broken down into products and waste. So most probably the efficiencies are often evaluated as the ratios of energy quantities and are often used to assess and compare various systems. So thermodynamic laws occurs within a system often are not accurately identified and assessed with energy analysis. In the today world, the growing energy supply and demand have created an interest toward the plant equipment efficiency and the optimization of the existing thermal power plants. So at present, most of the power plants are going to be designed by the energetic performance criterion, which is based on the first law of thermodynamics. So the energy losses taking place in the system can be easily determined by using a exergy analysis. So what is exergy analysis? So exergy is defined as the maximum amount of work that can be produced by a stream or a system as it is brought into the equilibrium with some reference environment. Or it can be thought as a measure of usefulness or quality of energy. Normally, so the exergy is consumed during the real process due to irreversibility and conserved during ideal process. So the irreversibility is the reason for the entropy generation. If you reduce what are the reason for the irreversibility or causes of irreversibility, we can easily identify with the help of the exergy. That is the way of identifying the exergy. Exergy can be easily identified where are the losses occurs. Normally, the first law of analysis only discuss about the energy conservation. What are the main energy conversion takes place and what is the amount of energy, useful energy and the various losses. But the losses we can minimize or the maximum work that can be extracted from the system we can use it, we can identify by using a exergy analysis. That is called as the exergy. Exergy is coined by in 1956 by Joran Ron by using a Greek word ex and ergon meaning from work. But the concept was later developed by William Gibbs in 1873. So exergy analysis is a practical approach to evaluate the merit of energy conversion or distribution process on systems. So with the aid of energy analysis, the performance of an energy conversion system cannot be evaluated efficiently and precisely. So that is the first law of thermodynamics. What is first law of thermodynamics is the complete conversion of the heat into work. But second law says that so it is not practically possible to complete the complete conversion of heat into work. So there will be some losses. So that losses we are not identifying in the first law. So these losses are identified using a second law. In exergy analysis, what we are doing, it is a complement to the enhance of energy analysis. It involves in the application of exergy concepts. What are the balances we can do and what are the efficiency? From that we can evaluate and improve the energy and other subsystems. So where the energy loss occurs and where are the points, what are the locations where the energy losses occur. So those things we can easily identify using a exergy analysis. It is a more, then we can identify it as a more beneficial opportunities through the wide range of processes and the systems, particularly for the evaluation of energy systems and the technologies, as well as an environmental impact in all existing thermal and nuclear power plants. So exergy analysis is a powerful tool for developing, evaluating, and improving an energy conversion system. So whenever we are doing first law does the energy conservation conversion system. So once the conversion system is there, we are day to day there will be a demand for the energy supply and demand for energy supply. So it is a we are going to improve the plant equipment efficiency and the optimization of all existing thermal parameters. That is a normal case. So what is our aim? Our aim is to improve the plant efficiency as well as the maximizing the power plant efficiency. How we can do the how we can maximize the plant efficiency? The only way is called as the exergy concept. So the exergy concept do the thermodynamic analysis of thermal process and the plant system. So it, in addition to the first law, insufficient for the in addition to the first law, it can be carried out with the help of a second law of thermodynamics. So in second law of thermodynamics, what we are doing, we are finding out the various losses. So once losses are found out, so we can identify where the losses are occurring. So these things can be identified with the help of the exergy analysis. Exergy analysis, we can find out that where is the maximum energy can be extracted from the each system. That is the we can do it with the help of the exergy efficiency. We are identifying the information about the assessing the performance of the energy system and where the losses, location, causes, and sources of deviation from ideality in a system can be easily identified with the help of the exergy analysis. In the exergy methods, when you can easily help to evaluate the thermodynamics values of the product. Energy forms in a complex system with multiple products. Example, cogeneration and trigeneration plant. So normally we are doing cogeneration and trigeneration plant. We have to improve the existing thermal power plant. So this can improve the maximizing the efficiency. Where also we can improve further more than 90%. We can improve with the help of the exergy analysis. Exergy methods can be economical and also it can improve the environmental things. Environmental assessments also we can carry out with the help of the exergy analysis. But it can improve the understandings of the energy conservation and energy crisis. So where we can apply the exergy analysis in the energy system. So the energy concepts are mainly applied. Everyone we know, utility sector we are using, industrial sector, residential and commercial sector, and transportation is the main applications of the exergy analysis. The application of the exergy analysis may be applied in the among the industrial energy system. Where we are applying the industrial growing needs in the industry, we have to minimize the losses. Whenever we are minimizing the loss, the efficiency will be maximized or electricity will be increased. Maximizing the industrial efficiency will be a main impact of the exergy analysis. Energy utilization of an efficiency of a macro system, for example, a particular region, city, or a particular state or a country can be assessed with the help of the exergy analysis. In the utility sector, so in the process industry such as electrical generation for both conventional as well as alternative resources, for example, solar, hydropower, biomass and geothermal wind. So these are the applications of the field. So generally the performance of the thermal power plants are evaluated through the energetic performance criteria based on the first of thermodynamics, including electrical power and thermal efficiency. The exergetic performance analysis can be only determines the magnitude and location and causes of irreversibilities in the plants. That is the main applications of the exergetic performance. The exergy analysis is it can determine the magnitude. What is the we can quantify and which at what point we have a losses and what are the reasons for the irreversibility. So these can be easily identified in the individual component. Okay, so this automatically can improve the performance and the efficiency of the particular system. In case of industrial sector, we can do it with the help of the, for example, the petrochemical, chemical and metallurgical process, heating and cooling system is the most complex for determining the overall efficiency and the effective values for the different uses of the energy. Exergy methods are used in many industries where it is a powerful tool for analyzing, assessing, designing and improving as well as optimizing the system and process. So what are the current research scenario in the thermal power plant? So largest source of electricity generation. It is still belongs to the fossil fuels. So today's after 2015, we have increased the use of renewable sources. That we have reduced the dependency of the fossil fuel. However, the dominant parameter is the fossil fuels only. So the largest share is electricity generation is because of coal, natural gas and oil. What the conventional thermal power plant based on the fossil combustion are currently facing a new challenges. For example, global warming, more emissions are there, more wastes are there. So how we have to reduce the heat loss? Mostly in all the thermal power plant, all the thermal systems, what are the major losses are occurring? The major losses are occurring in the heat loss only. So the heat loss, how we can compensate the heat loss is that is a current new challenge in the all the field. However, we are using a fossil fuel also. So in the fossil fuel itself, we are facing so many challenges. That is the main challenges is a heat. The utilization of the heat or the wastage of the heat is that we are unable to reduce the losses. But the challenges and recent activities result from the development of technologies, use of renewable sources and activities that aim to reducing the emission of harmful substances into the atmosphere. So the new challenges are a decisive impulse for introducing the challenges in a power plant and combined heat and power plant, as well as for implementation and continuous development of the new technologies allowing for the electricity and heat production in the least harmful way to environment. So here in recent years, we have observed many activities are carried out throughout the year as well as in the particular nation. They aim to reduce the emissions as well as optimize the performance of the thermal power plant. So we have to ensuring the continuous supply of the electricity and heat is necessary for a continuous monitoring of the all the process and conduct of maintenance and optimization works. So based on the data provided by the International Energy Agency, so the electricity generation during almost last 50 years, it's changing. Total electricity generation is increased almost 6 times. So when it reaches in, I have taken the data from the 2015, that is the 24,255 terawatt hour, with the share of fossil fuels around 65%. It is around 75% in 1973, but it is the dependency of the fossil fuel is reduced in 2015. We have to increase the go for a renewable sources. However, more dependency is on the fossil fuel only. The share of renewable energy sources include mainly geothermal, solar, wind, ocean, biofuels, and waste has increased from 0.6 to 7.4%, 1% of total electricity generation up to 2050. So the changes and intensive developments of the technologies based on renewable energy sources, fossil fuels still dominating. So the values presented in the diagram confirm the trends indicating the continuous use of coal, almost 39.3% in 2015 as the main source, and large increase of the natural gas utilization around 22.9% in the 2015. So these two shares are around 62%, 63% we got it. So still we are depending upon the fossil fuel. The usage of the fossil fuel is still dominating on. So that's why we are analyzing the Exergy analysis. Currently it is still dominating in the research field also. So now the domination of the conventional thermal power plant or improved thermal power plants in the Exergy analysis also is the main source for research projects or research PhD works. So what is the world electricity generation from 71 to 2015 by fuel we have given? That is the fossil fuel. It is dominating. Still the fossil fuel is dominating from 1971 to 2015. So here nuclear is hydro and non-hydro renewables and waste is a minimum amount. So in the below diagram in the chart, so here how much the energy is consumed. Energy is consumed is 6,131 terawatt hour. Here on the 2055 it is around 24,255 terawatt hour. Here still the dominate is the goal is still dominating. The natural goal is the second one. Natural gas is still dominating amount of 22.9 in 2015, around 12.1 in a 1973. So the oil percentage is reduced from 24.8 to 4.1 in the 73 to 2015. But the hydropower is decreased, and then non-renewable sources are increased from 0.6 to 7.1% from 73 to 2015. So here one of the important software used to analyze the Exergy, because most of the thermal power plants we are not going to directly assess the performance. So here all the thermal power plants are used, many devices are used. So in the physical presence or physical evaluation of the system is still challenging one. And moreover, the peoples are only the auditing persons are going undertaking the readings or analyzing the performance or optimizing the performance of the thermal system. But what we can do, we have a simple and economic and robust method. One of the software is called as a cycle tempo software. It is a flow seating software which can be used to model the steady flow thermodynamic system. So the software was developed jointly by the TU, that is a Delft University of Technology, and by TNO, the Dutch Institute for Applied Research. Since 2011, it is further developed and supported by a asymptote in close operation with the original developers, Delft University of the Technology. The primary aim of cycle tempo is to calculate the size of the relevant mass and the energy flows in the system. It is suited for the conventional power plant, compression, refrigeration and cooling systems, unconventional energy systems like solar, that is solar organic Rankine cycle power plants, and dry generation power plant systems, absorption cooling and refrigeration system, fuel cells, Kalina cycle power plants, and the SCCO2 turbine power plants, and ICGC power plants. So these are some of the power plants we can use it for a cycle tempo software. It is a few software packages that allows the Exergy analysis. So it has been around for more than a decade and has larger user community, including major energy companies and the consultancy firms and the research and development institutes using this cycle tempo software. So the main feature of this software is the calculation of all the relevant mass and energy flows in the system. So it is a particularly robust and efficient computational method, which means that you can depend on it to quickly obtain a reliable solution even in the most demanding situation. The cycle tempo can perform exergy analysis to provide insight into the exergy flows and losses within the subsystem, and allows to quantitatively compare losses of different nature. For example, fluid dynamic versus heat transfer. It is a fundamental tool when looking for the optimal system configuration and performance. The cycle tempo includes an optimizer that can find the maximum value of the merit of a parameter. Example, thermodynamic efficiency or a power output. The cycle tempo allows for real-time integration within existing plan-wide data monitoring system for performance analysis and troubleshooting. So it is applicable in many domains: mass flow, thermodynamic variables, chemical equilibrium, and compositions of mixed flows for the following process or combination of process: the steam turbine power plants, gas turbine, combined cycle plants, combustion and gasification system, heat transfer systems, fuel systems with low temperature as well as high temperature fuel cells, organic Rankine cycle power plant, and refrigeration system and heat pumps. So these are the applicable domains for a cycle tempo software. So here, so how we are defining, I am going to show it in the software also. Before that, we can see it. What are the symbol for the each device? These are the symbols we are going to use it in a cycle tempo software. This is called as a boiler symbol and reheater symbol. So turbine, two types of turbine. Then this is a condenser. This is energy equation code. We have two types of code. Then we have a flash heater. If you have a flash heater, we have a symbol like this. Heat exchanger, we have a symbol. The same flash heater, it is only the letter is varying. This is called as a deaerator. Deaerator, normally we are using it in a thermal power plant. Pump also nodal point. Source or sink. Second law analysis, we are most probably heat source or sink we have to use. So that is a del M or del V. That is a specified. And stack, this is a stack symbol, this is a combustor symbol, this is a valve used drum, then this is a steam drum is mentioned here, then reformer, fuel cells, then moisture separator, gasifier, scrubber, this is a separator, this is a reactor, saturator, so compressor, gas turbine, generator, motor. So those are the maximum symbols available in the cycle tempo software. What are the data? While we are discussing about the cycle tempo software, I'm going to give some input. We have to give the input. Normally in the CFD, we are doing some boundary conditions and input we are giving. Like that also here we have to give some input. So based on the input, we are getting some outputs. So P in inlet pressure, outlet pressure. Del P is a pressure loss in the apparatus. T in inlet. T out is outlet temperature. Del T is nothing but the temperature rise in the apparatus, because these terms will be given in the command window. So P in L, that is a pressure at the inlet of the pipe. P in is a pressure at the inlet, L is a pipe. P out is nothing but the pressure at the outlet of the L indicates the pipe. Del P is nothing but the absolute pressure drop in a pipe. So these are the various notations we are using. So del PF2, that is a pressure loss by flowing resistance. The flowing factor if we consider, this is the enthalpy at the inlet of the pipe, enthalpy of the outlet of the pipe. This L indicates for pipe notation. Del H3, that is a enthalpy drop in a pipe. T in L, the temperature at the inlet of the pipe. T out is temperature at the outlet of a pipe. X in is nothing but the mass vapor fraction at the inlet. X out is nothing but the vapor fraction at the outlet of the pipe. This is a prescribed mass flow. APNO is nothing but the apparatus number for which the estimate of a thermodynamic or a apparatus typical variable is specified. The DESMOS is nothing but the mass flow in pipe at design. And DESP is nothing but the average specific volume in pipe. So these are the notations we are going to use. So available mediums, what are the mediums we have to use? Because we are going to use a refrigeration cycle in case of a power plant, in case of a organic Rankine cycle. So these are gas turbine. Different streams we are using. Water stream, then potassium, then gas mixture, ideal gas mixture. Fuel means what are the fuel available, and water and H2O liquid, and is the ammonia water mixer. Refrigerant, single refrigerant or a refrigerant mixer. Liquids, secondary refrigerants. So these are the different medium types. What are the mediums? Because we are going to use the we are in case of while we are analyzing the thermal system in organic vapor Rankine cycle, we are using some organic vapor also we are using. About those things also we have to consider. And the system general data. So in case of this is a main general data. This is called as a new file, open, close, save, cut. So these are the open the torch. Here we have a run, print. So these are the thing. And here also we have a different data. So we are clicking the general data. The general data will provide the production function. Production function is nothing but the user-defined energy equation. Some cases, for example, while we are solving the problem in the thermodynamics, in case of Rankine cycle, so the power plant, the plant power is given. For example, 10 megawatt power plant or 100 megawatt power plant. About the production function, we have to identify the apparatus. For example, 2 is a turbine, means you have to identify the 2 with the 10 megawatt, or that 2,3 equal to 25 megawatt, or 2 is 10 megawatt, 3 is 50 megawatt. Like that, we have to identify if the value is given. If it is given, means we have to identify. Otherwise, if input is available, means we have to solve. For example, we are solving the problem in the thermodynamics. In case of a Rankine cycle, we have some problems we have to solve. The same kind of problem we can work out by using a cycle tempo software. So definition of environment. While we are analyzing the Exergy analysis, we have to define the environment. How we can define the environment? The pressure, temperature, and the chemical composition of the what are the things. For example, if you are using coal, means the corresponding component will appear. If you are using natural gas, the corresponding will come. If you are using the flue gas, the corresponding. For example, in case of gas turbine, we are using a flue gas. So the corresponding composition will appear. That is the function of the environment. So if we are defining the environment, then only we can do the Exergy analysis. If we didn't define the environment function, automatically there will be no Exergy analysis. That I can show it in the during solving the problem. I can solve it. I can show it to you. So now, auxiliary power concerns. For example, if the power consumers are not modeled, can be specified with the electricity concerns. Suppose we are using some auxiliary power devices. In some cases, we have to use. So that cases we have to name the system name and power gear. So normally it will be 0 only. So default 0 only. Yeah, otherwise, unless otherwise mentioned, no need to give the auxiliary power consumption. And general calculation setting. So before going to start any experiment, normally these things, in case of control button, in case of control of the calculation process, the calculation settings. For example, here the calculation settings. So here we have to do the settings. In the calculation settings, what are the things we have to off design factor, and what are the net frequency? What is the minimum number of iterations for a main iteration? Say maximum number of iterations, number of extra main iteration, those things. So here relative efficiency, how much? Minimum number of main iteration, maximum number of main iteration, number of extra main iteration, number of iteration with the under relaxation. So those things, net frequency, off design factor. So everything we have to give for the calculation settings. Okay. So now we are going to discuss about the software, cycle tempo software. I'm going to explain now. You can see how the software is operating. Yeah, I'm going to share my entire screen. So is it visible?
Yes, sir, it's visible.
Yeah. So this is a cycle tempo release 5.1. It is available in the website. Cycle tempo is available in the website. At the end of the session, I can show how we can download and use it. Now, using how we are working the cycle tempo software, we can discuss now. So at the end of the session, so where it is available, how we can download, I can show it, or during the question and answer session, we can see. So this no file is open. This is a initial thing. So just I have clicked the first one. So this is the open new file. This is a new file I have opened. So here I have shown what are the things are there, new, open, close, those things are available. So edit option, nothing is there here. So hide tools, show results, zoom out, so zoom extension. Here the general data I have shown in the PPT. What is production function? Here we can do the production function. Then what is environmental function? So these things we can define. For example, if you are defining the environment, it can take automatically. So then cancel. So then we have auxiliary power requirements. Those things we can give it here. Then we have a user defined input. If you have any user defined input, that is also we can give. In calculation, first thing settings, so that I can show it relative accuracy, minimum number of iteration I have mentioned, net frequency of design factor. So everything I have mentioned. I am giving okay. Then we have output control. So output control, summary of output we need, and no additional output is required. So flows in the pipe after each main iteration is not required. The final iteration is sufficient for us. And view, what are the things we have to be input, summary, text, output. So after we are running out, we can see all these things. Here it is not active. System efficiency, energy balance, combustion of fluids, heating value, applied fluid. These things are not active. Once we have evaluated the system, or once we run the system, we can get the remaining thing. So these things help, we can go through it. Using help, we can contents, what are the things are available. So under HTML contents are available. Okay, so these things are available. Everything, what are the things we can, energy sources, sink, everything, energy, what is energy equation code. So everything we can, the one we have to use one, when we have to use two. So everything is available here. So help also, using help also we can do. What are the apparatus? I can show what are the apparatus we have discussed. The boiler, how the boiler. So what are the data we can give? What is reheater? What is turbine? What is condenser? Feed water heater. So each device is available with some input and output data are available. We can easily go through it. Here this is new, this is open, this is close, this is we can save. So this is cut, copy and paste. So here we are finding option is available. Then here we have to run the device and print and these things. So these are the things available here. And in case of a right side top corner, we have a boiler. These are the turbines. So single point and multi-point turbines we can use it. So these are the condensers. And example for flash heater and heat exchanger. Then we have a deaerator. It's a pump. Then we have a junction points. If you need a junction points. So all the devices I have notified here. So if I want more devices, just you click on the toggle. Just you click on the toggle. So we can get additional devices. Sync. So additional devices. So if you want to come out of the particular things, you have to click on the arrow. If they click on the arrow means it will come out. Just select and give delete. So we can, if you want to delete, so just press it and we can delete. And we have a source. So what are the sources are there? Then heat sink is there. Then we have a stag, chimney, then combustor. So there's a flash heater, it's a drum, reformer. So whatever the things I have shown in the PPT, so all those things are available here. This is a moisture separator, is a gasifier. Example for gasifier. Then we have a scrubber, separator, reactor. Then this is example for compressor. So generator, and we have a motor also, and gas turbine. So this is a gas turbine. So the whole gas turbine setup is available. Just you click on this arrow, it will come out of this. So you have to select and give delete. For example, you select and give delete. So gas turbine, I can show it here. This is a whole gas turbine is there. We can do it, or we can design separately also. Okay. So just I want to go for new one. So before that, I have to close this one. Okay, now the new one has come. And so these are the below in the right side middle corner. In the right side of the right side, right side bottom corner, we have a streams are there. This is a water stream. So steam, flue gas, fuel, air. Then we have a gas, gases, liquid metal, shaft, user defined liquid also we can give. So here in this area we can have a search is there. We can type the text is there. Then we have to come out of the particular command and we have to identify these things. Once I have done, I can show it. This so once I am pressing this one, I am getting this one. So this point is used to identify the pressure, temperature, enthalpy, and mass flow at the particular location. So that is the advantages of this software. So now I am going to find out the first thing we are working out the performance of the boiler alone. So first device is the boiler. So boiler, what are the things are need? Boiler need some heat source is required. Some heat boiler is it itself can produce a heat. So boiler itself produces a heat. But here what we are doing, so here we need a three sources are there. Three sources are there. So this source or sink. Here the source for water source for another two. One is called as a boiler. But here we have to connect with the water. Just to click on the toggle switch. So this is a water. Water is connected to the boiler. So another water is connected to the boiler. But these two are a water. So what the output of the boiler? Input of the boiler. This is the input. So the input to the boiler is water. Okay, we have two sources are there. Here we have one source. Here we have another source. So these two sources are connected to the boiler. So what is the outlet of the boiler? Outlet of the boiler is steam. You have to select the steam here, and you have to connect these 2 points. You have to connect these 2 points. So you have to press on the click arrow and you click once again and you delete it. So once again you have to connect from this point to this point. Straight away we can connect. So this is a point. These are the three things we have connected. 2 and 3 is water. The 1 and 2 are water and 3 is called as these are the pipes. These are the water pipes. These are the water pipes. 1 and 2 are called as a water pipes and 3 is called as a steam pipe. And 2 and 3 here 1 is boiler. 2, 3 are called as the 2, 3 are the water source and 4 is called as the source for absorbing the steam. So those things we have selected. Now what we have to do, we have to give some input. Here just you click on this one and we give input to the device. So first device is a boiler. Just you close it. Second device is a source or sink, water source. Third device is a source or sink. Fourth device is a source or sink. But we have to give a minimum possible inputs that can be used to evaluate the performance of the boiler. What are the possible things we can give? So for boiler, we have to define. In boiler, I have to just double click on it. Just double click on one. In double click of one, del P. The del P is 2 bar. The del P is 2 bar. Del P is nothing but the pressure difference is 2 bar. Boiler, the pressure difference is 2 bar. And what is the temperature out of the system? Here input we are giving the water. So the output is there is a difference between the in and out of the pressure is 2 bar. The del P indicates that the difference between the in and out of the pressure is 2 bar and the temperature out of the system is 400 degrees. So any value I can give. Now I have given 400 degrees Celsius. And lower calorific value of the fuel. For example, here I am giving some 20,000. And Exergy of fuel, that is a 510 kilojoule per kg. So those things I have given. Then 2 is a source. So in the source, what is the pressure at which the water is leaving? It is a 50 bar. The temperature at which water is leaving is a 40 degrees Celsius. What is the del M? Del M is nothing but the 11.42 kg per second. The enthalpy out of water is, so those things we can identify from the steam table. Enthalpy out of the system is 176.3 thing. And fourth, I am not going to give any data. Why I am not giving all the data? Because the outlet of the boiler I have defined. Automatically it will be input for the source or sink. Suppose if you are defining the losses only, Here we have to identify. So the data I have given. So now I have checked I have to run the process. So error, I am getting one error. So what is that error? So the total number of equation to calculate the mass flows in the system equal to the number of pipes. So I didn't give any output for the number of pipes. So that's why it is showing. I am identifying steam. Here what it is? It is a gas mixer. So add composition. What is that? It is a add composition. What is entering here? It is a, sorry, wait. Here steam is there. Here nothing we have to give. Gas mixture. You no need to give any composition. So it can take water or steam. That is enough. IP97 water or steam is enough. Here already water is there. Now we can run the equation. Again I am getting error. So I am changing the parameter lambda for a combustor you have to give. So in case of a system 2, I have to identify what are the things I have given. System 2 P out is given, T out is given, del M is given, system 2 del M is given. So del M is some 10 kg per second. Here the H out equal to 213.63 kg per second. Just I have changed here. Here nothing we have given for 3. So that's why it is showing error. For P out equal to 100 because so we have two different things. This is a normal feed water. This is the feed water recycled from the previous sources. About those things we have to identify. The temperature, we are increasing the pressure. The pressure is increased before entering into the boiler. About those things we have to identify. So here del M equal to 11.42. Here the H out equal to some 176.37. So based on the things we have given, we can identify these values. So now error is 0. Here it can show what are the criterion absolute deviation, what is the maximum absolute number of evaluations. So everything we can see it here. So here, so what are the things we can identify? So this symbol used to identify the values at this point. So it indicates, so this is what is nothing, this is nothing but the previous case we have seen. So what is P? This is a pressure value. This is a pressure value, enthalpy, mass flow rate, temperature. Pressure, temperature, enthalpy and mass flow rate is shown here. Here, what is the lower heating value and boiler efficiency? Here we are assumed 100%. That's why it is shown as a boiler efficiency. At this point, what is that? So what is the pressure? Pressure, temperature, enthalpy and mass flow rate. So this point also we can identify. So these are things we can identify. In addition to that, we have to go through the calculations, the view. In the view setting, we can see the text output. Text output is there. Then we have system efficiency. What are the various systems? So boiler only we have identified it. So what is the power absorbed? The energy, the boiler, the energy equal to 64 megawatt energy generated. The boiler absorbing the 64 megawatt to produce the steam. That is the one thing. Then energy balance. What are the things are there? What are the devices we have used? Here we can see what are the devices we can use. Boiler we have used. Source or sink. Two is nothing but the source or sink. So another 3 is also a source or sink. So 4 is also a source or sink. Nothing data we have provided by the 5. That's why it is 0. So what is the energy loss? Energy loss is nothing but the amount of heat energy absorbed. So that is a 65 megawatt. Source or sink, how much heat is absorbed? So it can absorb the amount of enthalpy. This is the energy loss, the total energy, lower heating value. Those things we can get it because once the water is absorbing it, then it becomes a steamer. So those things we can easily identify. So what are the each devices? What is the positive energy? It is absorbing. That's why it is negative. It is generating or it can absorbing it can receiving the steam. That's why it is positive. But these are the various devices. What are the energy balance? So data for all pipes. For water steam, we have specified For specified data, what is the entropy value and the enthalpy value? What is the entropy? We know, measure of irreversibility. So those things we can get it from here. Then losses in pipes. So again, nothing we have identified, only pressure drop only, and temperature drop will be identified. So that's about the simple boiler device. So here, when I open the first thing, this file is open. So in here we have to identify all the view. The view item is available here also. That is the table. That is this table. Here we can see what is the energy balance available. The same table will appear. Data for all types, losses in pipes, the system efficiencies. So everything is appear here also. Text output. So input summary. Well, input summary is nothing but what are the input I have given. What are the input I have given? For D out is 400, boiler. LHV I have given, Exergy fuel I have given. So everything we can see it. So that is the function of this one. Suppose if you define the environmental function, we can get the Exergy analysis also. Sorry. So is my window is visible, sir? Is it visible?
Yes, sir.
Okay, thank you. So here, once I have identified the environmental function, here we can find out the Exergy analysis also. So just I am going to close now. In the environmental function, I am going to delete this environmental function. Now I am giving OK. So now I have to run it. So warning 0, error is 0. So just I am going to see the view option. Here you can look at Exergy value. No Exergy values are calculated. Why it is showing means because I didn't define the environmental function. So that is the advantage of this method. Energy and exergy flow. No energy and exergy flows of pipes are calculated. Why it is showing like this means I didn't define the environmental function. By how to define the environmental function? So once I define the environmental function, so I can get the again I have to give run. So once it is successfully run, you have to go through the energy and exergy. Now we can see the what are the total energy flow, thermal mechanical energy flow, chemical energy, total exergy flow, thermal mechanical exergy flow, chemical energy. So those things we can view. So once we are defining the environment, if nothing is defined in the environment function, we won't get anything. Here also for pipes also, for each pipe, source, sink, for all those things we can calculate the exergy transmitted from the system and the relative exergy losses also. So that is the advantage of the cycle tempo software. So here what we can do, how we have to use it for. So here a simple device I have taken. So you have continuously you have to change the input. So what I have given here, just I have given only one input. Just we are defining or continuously changing the input value. Automatically we can get the change in output value, or we have to improve the efficiency and what are the exergy losses in the particular point. So everything we can identify. So those values we can take it for the consideration or optimizing the power plants. So here again how we can save it. Just you go and sorry, it is opened, not here. So here we have a save option is there. So it is coming it as a no name. But I am going to give it as a boiler. BOIL. Here already boiler is there. So boiler 1 I am giving or boiler new. So something you have to name it. Yeah, this is the first device. Just I am going to close it and minimize this one, input summary. So next I am going to do the analysis of the another one. So next device we can do it for a combustor. So we have to check where the combustor is available here. So we have a combustor here. So these are the combustors. Okay. So you can press this arrow or just escape. Just you have to click escape and delete. So it can be removed. So now you have to take the combustor for analysis. So for combustor, so what are the input need? We need to give some solid, liquid or gaseous fuel and air is required. Yeah. So these are the two inputs. We have to get some output. Output will be connected to this system. What are the inputs are there? So one input for a fuel, another input for air. The output is a source or sink. It can get the flue gases. So this is a simple combustor device. We have it. So now Here we are defining. I'm going to give some stream here. What we have given normally in today's world, combustor gives a gas. The gas element is given, and we need a air for combustion. Here we have a air is there. I have selected air. I have given. So if we are getting like, just you can adjust. So if it is not properly located, we can, there will be, yeah, it is correct now. So how I have taken, so in the second toggle button, so here I have water, steam, flue gas, fuel, air is available. Then I have a gas, gases as liquid metal, shaft, user defined liquid is there, and user defined vapor is there. So first I have selected the gaseous medium. Next I have selected the air. Then what I am getting here, so once we are burning gas and air, so here we are the product of gas and gaseous fuel and air will give the flue gas. So you have to select flue gas also, where it is available, here it is available. So you connect and change it here. So these are the devices. First combustor I have it, then I selected the two sources for input, one source for output. This is the combustor device. So now I have to give input. So just you click on this arrow symbol. Now we will get this arrow plus symbol. Then I have to give input for the combustor. So combustor, you are giving the energy equation code. This EEQCOD is nothing but the energy equation code. The energy equation code we have to give it for the condensation or evaporation as well as the combustion also we have to give. So the energy equation value is 2, and lambda value you have to give it as a 1. So this is the estimated accident and fuel ratio. This I am giving 40. And the reactive pressure, the P react is nothing but the reactive pressure. The reactive pressure is 10 bar. So these are the things, because when these are the minimum input required. Energy equation code you have to give. The equation code will identify whether it is combustion or condensation. And the lambda value you have to give. Estimated accident fuel ratio you have to give, and the reactive pressure we have to give. Then P out. What is the value of P out? 10 bar you have to give. P out equal to 10 bar, and the temperature out equal to 20 bar. So temperature out is, sorry, it's not a temperature out. This here we are giving for combustor. For combustor you have to give energy equation code is 2, and lambda equal to 1. Estimated accident fuel ratio is given, and reactive pressure is given. So these things are sufficient for us. Next we have to give it for the gaseous fuel. So first thing I have given it for combustor. I can show it here. Combustor, what are the things are there? This is a combustor. In the combustor energy equation code I have to give, and lambda value I have to give. The estimated accident fuel ratio I have to give, and the reactive pressure I have to give. This is over. So just a minute, sir. Chandru, meeting where they So next we have a 2 is a source or sink. For source or sink, we are giving what is the pressure at which the gas is leaving. The pressure at which gas is leaving is a 10 bar. The temperature at which the gas is leaving is a 20 degrees Celsius, and the mass leaving is minus 10. I am giving. Why I am giving minus 10 means the minus sign indicates the flowing out of the system. Minus sign, minus 10 I have to give. So these are the data sufficient for the source. Next we have a air. So air data we have to give the same pressure. So the same 10 bar pressure the air is coming, and the temperature of air is around 15 degrees Celsius. I have to give it. We have to give it for a source or sink. So what is the temperature pressure at which the flue gas is coming? So here I am giving 10 bar P in. I am giving. Why I am giving 10 P in? So if the P in, the flue gas are receiving. Here the receiver end. These are the leaving. These are the center point. These are the center. That's why I have given out. So it is receiving. That's why I am giving in P in. So these are the data I have given. Just I am going to run. What it is again? The pipe 1 to no medium data is specified. Actually, pipe 1 to we are defining. 1 is a gas, 2 is a air. So I am not mentioning anything. So however I am giving continue. What is source? Here it is reading a error value. Why the pipe number 1, 2, 3, no medium is specified. Upper the least data is less data is available for computing the medium type for the cycle number 1 of the system. Upper I have to close and so before run it can show the some warning it shows. So then what I have to do? I have to identify the medium. You just click on the pipe, double click on the pipe, it is a gas. So auto detect. In auto detect, you have to select a gas mixture. Here you can see what are the things are available. IF9 on water or steam, gas mixture, solid fuel, potassium, ammonia water, refrigerant, and liquids, TPSI, free stand mix, user defined. So many data are available. Here what are the gas mixture I have to collect. So then add composition I have to give. What are the composition? This is a standard natural gas I have to select. So once I am selecting the standard natural gas, then only I will give this C2, H6, C3, H8, the standard gas mix, standard natural gas. What are the things are available? It automatically select. Suppose I am selecting some air. Air means it can select the yes means if you give yes means it can automatically change it. Natural gas means it can change it automatically. Once it is an or composition panel also available. We can select from the composition panel also. This component panel is there. Here also we can select it. So just you click on the OK. So here give OK. Then I have to give run. Now also the pipe number medium 2 is not selected. Just I am giving again it shows the error because pipe number 2 is not specified. Then I have to close and select. I have to select the medium on 2. Symbol is that is you can check here. Number 2 is this is number 2. Symbol is symbol I have taken from here. Then color add here add extra condition is also there. Suppose if you want to give some data for pipe also we can give it here. What is H in, H out, P in L, P out L, that I have shown in the PPT. We have seen in the PPT. Here also we can do it now. So here also we can do it. But we have given the data for already for 2, 3 and 1 and 4. That's why no need to give it for pipe. So wherever the availability is there, we can give it also. Of design input, everything we can give. Now I am going to select the type of data. So what I have to select again gas mixture. Then I have to give a add composition. So what it is there? It is a standard air. Because here we have 2 is a air. Of a standard air I have selected. Then I have given OK. Then here also OK is given. So now I am going to run. Here also it is once again showing the error. So what where it is missing again the pipe 3 is not specified. Flue gas. Here again gas mixture. Add composition. So here you have to select the standard flue gas. OK. Then here you have to give OK. Then you have to run. Again we are getting the warning symbol 1. So error is 0, but warning we got it. So warning we have to evaluate where we have did some mistake, and then we have to go through the. So warning is 1, but the program is success. So now I'm just checking whether all the parameters are received. Yeah, it is a no error. That's why I'm getting like this. So one more warning is there. So the reason for warning I can explain now. So why that it shows the warning. So here the gas pipe should reach this point. Okay, so that's why it is showing some error. So just I have to delete it, and the gas pipe I have to select because the gas should enter the medium, because we have to give like this. So now I am going to run again. It shows the error. Why it is error? Because I didn't mention the gas. Up I have to select the gas here, gas mixture, then add composition, then standard natural gas, then give it is OK. Here OK. Then you have to give run. So warning 2 is there. What are the warning is there? Just we can check it later. So warning again, the warning we are getting, but the system is working successfully. So warning we can evaluate later. So what is the input? So this point we can take, or we have to select this point and delete it. You have to identify this point also. Identify this point also we can get. Here we can go for a energy balance, though energy and exergy flows are there. The reason is we have not defined the values. What you can do, so just you have to define the, here nothing, we have defined of the lambda we have given, the estimated pressure and those things we have given. Nothing is there. Here we can give the environmental function, we can give it for a energy and exergy analysis. So now I have to go through the view. We can get the energy values and exergy values. So if error is 0, automatically we can get the output. No need to worry about it. So the output we have obtained. The total energy flow, what are the chemical exergy, thermal mechanical exergy, total exergy flow, chemical energy, everything we can identify. So here you minimize this window. Here also we can see what is the losses in pipe. So pipe means nothing we specified it. So here what are the data for all pipes, we can take it. So these are the data for all pipe. We can make it as a Excel also. So that is also possible. This is energy balance. Energy balance in this case. So messages nothing but the what are the how many iterations are there, what are the warning symbols are there. So the calculation is finished normally. For here the warning may be some elimination may be occurred. So those things we can identify it. Okay. So input summary. What is input summary? I have given. This is the input summary for the given all the pipes. So here I have to, here this, what is this rectangle indicates this is a P, pressure, the temperature at which it is, and after combustion the temperature is reached around 214. So what are the input we have given? Just we have given the input of, just we have given the input of the equation code lambda, the estimated accident fuel ratio and the reactive pressure only we have given. And what are the output condition? What are the gas is leaving, the pressure at which gas is leaving, temperature at which gas is leaving, the del M we have given. Here also the air pressure and air temperature we have identified. Here in this fourth point only what is the input and here the what is the in at which the flue gas is coming. So those things we have identified. So for that thing the exergy equation may calculate what is the pressure, temperature, enthalpy and mass flow rate. So those things it can evaluate. Okay. So here also we can save it as a combustor. So just to save it. So combustor. Already combustor is there. I'm giving combustor one. Next we have a next device is a compressor we can define. Just you click on the first one, that is no name. We have a compressor. So just if you want to change the position means, so you have to right click on it. You have to keep the plus symbol near to the point. So just you right click on it, it can rotate. It can move automatically. Okay. Now we have a compressor. So what is the input for compressor? Input for compressor is air. Output for compressor is also air. Input for compressor is air and output for the compressor is also air. Okay. So just click on this arrow, it comes out of it. So now we have to define what are the terms are there. So now before that we have to connect. So what is input? Input is air. So what is output? Output is also air. Okay. So just we have to come out of from the particular toggle. Then we have to define the pressure ratio. So what is the compressor is increasing the pressure. What is the pressure at which the air is coming out? That is a P ratio. P ratio is nothing but the pressure ratio. And what is the isentropic? Isentropic. This ETHKI is nothing but the isentropic enthalpy. So isentropic efficiency, not enthalpy. This is the isentropic efficiency. This is a mechanical efficiency. This is a electrical efficiency. Over here, I am giving this efficiency of 50%. That is 0.5. I have given. I have given this value. Then, what is the inlet condition, input conditions? What is the pressure at which the air is leaving? That is the atmospheric pressure, 1.013. The temperature, atmospheric temperature, we can take it as a 15 degrees Celsius. What is the mass at which it is leaving? 10 kg per second. So these are the input. Here we have specified two conditions. No need to specify anything here, because already we have specified what is the pressure at which it is coming. We have specified the efficiency. We have specified. So these things are sufficient. So now I am giving a again no pipe medium is specified. So you have to specify the medium. Gas mixture, add composition, standard air, okay. Again give run, warning 0, error 0. Okay. Now we can check what is the pressure, temperature, enthalpy and mass flow rate at which the air is entering. 1.013 bar, the temperature is 15. This is the input we have given. Enthalpy it is calculated and mass flow rate we have given. So what is the temperature at which it is leaving? Leaving after compression. So we have given the pressure ratio is 15. So the pressure is 1 bar is increased into 15.19 bar. What is the temperature increase? For when the pressure is increases, automatically the temperature is also increasing. Flow rate. Suppose I want to check it here also, you can get the same value. You can see, compare here. So this outlet of the compressor is equal to input to the source. So here the same value we can get. Suppose if any pipe losses are off design condition we have specified, automatically the value will be changing. So in the industrial sector, the pipe loss will be considered. So those time we have to give some extra inlet, that is the off design condition or extra inlet conditions we have to give. Normally we can get, just press on it. So now go and see the, so view what are the data are available, or instead of seeing the view, here also we can see what is the system efficiencies. So what is the power system efficiency? This here it is shown for only boiler, it is showing. So now we can show it for the system efficiency for compressor. How much it is? 77,000 kilowatt or 7 megawatt. Then energy balance, sinks, how much energy loss, and then energy loss in the source or sink or compressor. So those things we can evaluate here. Then composition of fluids. So what are the things? What are the things we have given? From that we can get the composition of fluids. Heating values, nothing we have specified, 0 we will get. Data for all pipes. Gas mixture we have specified, that is the air. So further, what is the enthalpy, entropy and temperature we can see. So data for all pipes we have discussed just now. Then rotating equipment. What is the compressor? Is a rotating equipment. The corresponding isentropic efficiency, that is we have given. We have given this isentropic efficiency is 50%. That's why it is reflected here. Here we have given the isentropic efficiency is 50%. The same value is reflected here, 50%, and mechanical efficiency is 100%. Nothing we have given, it is taken as a 100%. And motor and generator, only compressor we have identified. The mechanical conversion efficiency is 95% is taken. So and the graph also we can specify. Whatever the graph you have to select and we can give a new table or new value, whatever the things we can identify here. So I am going to say this is a compressor. So compressor is again I worked out already. So compressor 1 I am saving it as a compressor 1. It is appear as a compressor 1. Okay. So next we have a condenser. So select condenser here. Yeah. So condenser. So condenser is operating between the, here the steam is entering and steam is leaving. So for that we need a cooling circuit also. Here we have one more circuit will be there. But here condenser needs a, here we have one inlet, one outlet. Here another inlet and another outlet. But two inlet and two outlet we have it. But here we need a source and we have to define a source and a sink. So source and sink, and here also we need a one source. In addition to that, we need a pump also. For cooling tower, we need a pump also. We have to specify. Now, so what is coming out from the turbine? The coming out from the turbine is a steam. The steam is converted into water. So the steam is converted into water. Okay. So here is the steam. Steam is converted into water. So how it is conversion takes place? Because of condensation. So for condensation, we need a cooling tower. Cooling tower will take the cooling water, the cold water from the help of the pump. So from that, it can be circulated through the condenser, where it can absorb the latent heat of vaporization and it becomes a water. This is a cooling water circuit. This is a cooling water circuit. Here the two sinks are the two source and sinks and one more source and one pump is required. But here we have to specify the medium. First we have to give the values for condenser. First you click on it. So click on the condenser. Condenser, for condenser it is a cooling process, CU code 1. So the pressure at which the entering is 2 bar and leaving is 3 bar. Entering is 3 bar and leaving at 2 bar. So what is T in? So temperature at which the water is coming, it is a 20 degrees Celsius only. So the del T1 is equal to only the temperature is 5 bar. And the del P2 here 0. And the saturation code we have to give. If it is a water means just saturation gear you have to give it as a 0. So these are the conditions given with respect to condenser. What is P in? Inlet. So V in, P out. What is T in? What is del T or T out we have to specify. And del PT, the time press, this is a del PT, that is 0. And the saturation code we have given, just press OK. Then we have a source. We have a source for a steam entry. So what is steam entry? After expanding all the steams, the pressure is around less than atmospheric pressure. We know this 0.2, 0.1 bar, 0.3 bar. So those things we know. The mass flow rate is some 5.5 kg per second. The temperature at which steam is leaving is some 80 degrees Celsius. These are I have given. These are the conditions for the steam out. Steam out. Then condition 3. 3 is nothing but the, again we have one more source. So what is the temperature at which water is coming? Almost 40 and del P equal to 0. There is no pressure. There is here the temperature at which the water is leaving is 40. So then you have to give OK. Here in this source the del P almost 0. No need to give any data because already almost the data are given for the condenser. Here it is a circuit. In this circuit we have provided the data. So no need, just del P is alone you have to give. For pump you have to give some enthalpy equal to 0.9 you have to give, and the mechanical efficiency some 0.89, 85 something you have to give. So those things you have to give it. So these are the data we have provided. Now I have to run. So error is 0, warning is 0. Then I have to go for it here. Here, so this point, these are the data we have provided. What are the data I have given? The pressure I have given, mass flow rate I have given, remaining data it calculates. It is calculating. And these are the input I have given. These are the output for the source and sink. But pump output is totally different. This is a pump output. So this is the input for the condenser. And these are the outlet for the input for the source. So condenser also, how much the temperature? 20 only I have the low and high temperature difference, it can automatically calculate. So you can look at here what are the things are there. So these things are defined here. And in view button also we can see what are the things are there. Data for each pipe you can see. Because we have number of pipes we have increased. So volume flow rate, mole flow rate, mass flow rate, the pressure, temperature, enthalpy value. So those things are available. And here losses in pipes. Loss in pipes, nothing we have mentioned. Rotating pump alone, rotating equipment. And heat exchanging equipment, again condenser. Here we can see the system efficiencies. What is the auxiliary power consumed and consumption, we can go through it. And the energy balance we can see. So condenser and the pump and the source sourcing. What is the energy absorbed? Energy absorbed and energy released. These things is mentioned here. So suppose if we given a environmental function, automatically energy and exergy flows will be calculated. So those things also we can give. If you want to give the environmental function, you give just OK. Then you have to run it and you can give the energy and the exergy flow. So go to the view and the energy and the exergy flows are available. So before that it is unable to click on it. Now once we have defined the environmental function, automatically we can get the values. What is the each exergy transmitted from the each system we can calculate. So if I want to save this one, just you click on it and I have to save it as a condenser. Condenser is already there. I am giving it as a condenser 1. So these are the simple systems we can operate. We can operate and find out the energy and exergy flows. So next we have a heat exchanger is there. One of the simple device we have a heat exchanger. Just I want to change the direction, I have to right click on it. So just I have to right click on it. Just right click on it, it will be automatically changing. So this is a heat exchanger. For heat exchanger, we have to give what is the in for heat exchanger, out for heat exchanger. In addition to that, so what is the flowing here? Here the flue gas flowing, here water is converting. Here we have to give a stag. So stag you have to keep it here. So for example here, heat exchanger, here one fluid is flowing, opposite direction in a cross flow direction we have another fluid is flowing. So this will exchange the heat. That is a function of the heat exchanger. So here we have to give what are the flows are here. Here water is entering here and leaving. Water is entering. This is a direct point and the water is leaving at this end. So what is the heat exchanging medium? Heat exchanging medium is a flue gas. The flue gas entering here and leaving here. So these are the things we have taken. So here what are the inputs we have to give? So in case of a heat exchanger, so heat exchanger we have to give. This is a exchange heat. Energy equation code is 2 and del P1. That is a del P1 equal to you have to give some 3 bar. There is a pressure loss and del P2 in the water. The water is the loss is minimum. Okay, yeah. So we have to give the pressure loss and del TH. So the loss in enthalpy we have to give because directly it is a flue gas. Second one is a source. So here water source. So what is the pressure at which water is leaving? Some 40 ppb and the temperature at which the water is leaving is a 120.7. The del M equal to del M is nothing but the mass flow rate you have to give. Mass flow rate you have to give. So these are the conditions for heat exchanger and source or sink. Here I have given for apparatus 2 I have given. Now it is okay. Then we have to give the input for the apparatus 4. 4 is nothing but the flue gas coming out. So flue gas coming out at what pressure it is coming? It is 1.013 bar. And the temperature is around some 270 degrees Celsius. and del M at which it is leaving is minus some 130 kg per second. 130 kg per second. Okay, so these are the data are sufficient. No need to give any data for stag because so here here we have specified for the conditions for the heat exchanger as here, and also for the sink also we have specified in a heat exchanger. Just we can run. Okay, here there is no medium is specified. Then you have to specify the medium, gas mixture, add composition. The composition is a standard flue gas. Then okay. Here also already specified. No need to specify it once again. That is sufficient. We can check once again. Warning is 0. So now we have to check. We have to check what it is leaving. So inlet conditions. What is the temperature, pressure? Because the pressure is increasing, because the water is converted into increased high pressure water. High pressure water. Some cases we can take it as a steam also. The condition at stag. What is the condition at stag will be there. Here. So those things we can get it here. So both will be same because there will be no losses specified. Here the both will be same we can get. Here we can get the change in values. So here view settings, you go and get the heating values. Nothing we have mentioned that's why there is no heating values. So energy balance. What are the energy balance for each device is given. So those things we can get it from the given data. Again, if you want to get the here energy and the exergy, we cannot click. Why we can't do? Because we have not defined the environmental function. We have to define the environmental function and say yes and okay. So once again, you have to run the component, run the simulation. Now you go and see the view option where energy and the exergy values are appearing. Energy and the exergy values are appearing, where you can get the efficiency, all the efficiencies, all the energy and the exergy data, everything we can see. Here the efficiency, universal efficiency, reference functional exergy efficiency, everything we can get it here. Now I am going to save this one as a heat exchanger. So heat exchanger is already available. Off design is available. Simple heat exchanger is available. I have worked out already. So again heat exchanger one I have save it. Now I am going to close this one. And one more device we can see. So the gas turbine. So gas turbine, what are the devices are there? Gas turbine. I need compressor. Then I need for compressor we need a source. Compressor we need a source is required. Then after compressor, the air is compressed. Where it is going? It is going for combustor. We have a combustor. So once it is combusted, we have to expand the flue gas through the turbine. Then we have a so the flue gases are exhausted through the stag. So whenever we have a turbine, we have a generator will be there. So these are the minimum number of devices required, and one more source is required for the combustor, because combustor near the air and fuel input is required. Air and fuel input is required for it. Now we are going to apply. The input conditions. So before that we have to connect the compressor and turbine and generator. Okay. So next for combustor we need a air. Air is required. So first air is there, and the compressor air is connected to the combustor. So we need a fuel. What is a fuel? Normally you have to take the standard flue gas. then now standard gas, natural gas. So after burning, it will be converted into a flue gas. So flue gas are expanded through the turbine. After expansion, it is connected to the stack. So these are the gas turbine. This is the gas turbine. Now we have to specify the conditions. So what are the conditions we can give it for compressor? So the compressor, the pressure at which the air is leaving around 13.8 bar, around 14 bar. So enthalpy is equal to some 0.85. I am giving isentropic enthalpy, and mechanical efficiency I am giving 95%. I am giving 0.95%. So these are the minimum data required. Then I am giving the data for the source or sink. So that is the atmospheric pressure. Atmospheric pressure, the air is entering. At atmospheric pressure, the air is leaving out of the system. And del M is around some 500 because it is a gas turbine. More mass flow rate of is to be given. So these are the outlet. These are the outlet condition or input for the compressor. So air it is taking from the atmosphere. That's why I have specified the atmospheric condition. It's okay. Then third, we have to give the data for the combustor. So combustor energy equation code heat, it is a 1. The del P for 1 equal to 0.27 bar. The del P for 1 equal to 0.25 bar. The estimated accident fuel ratio is equal to some 25. And here I have to give the reactive temperature. Here, why I am giving reactive temperature? Reactive temperature playing major role. Here the pressure is. That is why here we have P react. Here P react. So those things we have to give. P react also we need, because at what pressure it is giving, then only we can calculate the enthalpy. So these are the input required for the combustor. Then we have a turbine. So for turbine, so what is the temperature at it is coming? Already we have defined it as a 1100 degrees Celsius. And the enthalpy equal to isentropic enthalpy equal to some 85 we can give. Here we can give some 0.92. It's a mechanical efficiency somewhat higher, 0.97 we can give. So these are the data required for the turbine. And we have to give the data for the stag. At what pressure it is coming? It is entering at the atmospheric. Again, after expanding all the gases at a high pressure, it is expanding through the stag at the atmospheric pressure or less than atmospheric pressure. And here also we have one more source is there. So for this source, what is the pressure at which the gas is coming? The natural gas is coming out from the 15 bar, and the temperature is around 15 degrees Celsius. And we have to give some lower heating value, LHV, we have to give. The lower heating value of the gases required, then only we can calculate the energy and the exergy for this gas. In addition to that, we have to give the generator efficiency. Generator efficiency is around 0.98%. We have to give. So these are the minimum data we have give. So here you have to run the command, because here there is no pipe medium is specified. Then you have to go gaseous medium and not auto detect. Gas mixers you have to select. In the composition you have to select the standard natural gas and you give it okay. So then it is okay. Here air you have to give. Air you have to give the air, we can leave it later, we can give. So here we can give the here auto gas mixer, add composition, and you have to give some flue gas. Okay, here okay, then you have to run. Again pipe number 1 is not specified. So if we specify pipe number 1, automatically it can take the value. Pipe number 1 again gas mixer, add composition. Here it is a standard air. Okay, it's okay. Now I have to run the thing. I am getting one more error. What is that error? So I have to go through it and so all the medium we have specified it. Here auto direct gas mixer composition. You have to give standard air. Okay. Okay. So here whenever we are giving lower heating value, you have to define the environmental function also. So the environmental function you have to define and give okay. So in turbine, you have to give some So this GD code you have to give it as a 1. Turbine, you have to give the GD code. Again it is showing some error. So we have to check once again. Wait a minute. So here this already I have evaluated this one. So because of time constraint, I am showing the existing one only. Here we can check what are the data are available. Same data are available. The pressure out, the enthalpy and mechanical efficiency is available. And the second one is the source or sink. What is the pressure at which it is leaving and the temperature at which it is leaving, and del M we have specified. Then third one is the combustor. In combustor I have specified what are the things. EE code I have given, del P I have given, the estimated accident air fuel ratio, and the T react and P react is given. Here what is the GD code I have given, T in I have given. Then enthalpy, both the enthalpy, mechanical and isentropic enthalpy is specified. Then we have a data for stag, and we have to provide the data for the gaseous medium also I have provided, and the generator is given, and the environmental data function also, environmental definition also I have defined. So here the error and warning is 0. So here we can calculate what are the things are available, energy, exergy, and what are the points we can calculate. This is what is the pressure power in for turbine, generator, and data for stag, and data for turbine inlet, data for combustor inlet. There is a air outlet. There is a air outlet we can calculate, and compressor inlet we can calculate. So these are the various value we can get it from the equation. And the energy balance also we can obtain. For a system we can obtain a energy balance, and the energy and the exergy values, and the efficiency, all the relative efficiencies. So those things we can get it from the above system. So I have more number of problems. Because of the insufficient time, I am going to conclude this session. Sir, Ganesha.
Thank you, sir. Sir, thank you, sir.
Sir, I thank the management and the principal and the head of the Department of Mechanical Engineering and the coordinator Sangar Ganesha for allotting this session for energy and exergy values in a simple thermal system. I thank the management and the Department of Mechanical Engineering and the coordinator. Thanks. Thank you once again, sir. Thank you, sir.